I'm going to go ahead and share my screen for 8.4. Okay. And so this is kind of where we left off on Monday. Okay. We left off thinking about circles and how sometimes the circles are symmetric about the x-axis and how sometimes circles are symmetric about the y-axis. Um, and one thing that I think is helpful in me remembering which one is which is if you think back to the unit circle, all right? So on our unit circle, the x coordinates and the y coordinates are actually the same as the cosine of an angle and the sine of an angle, right? And so it shouldn't surprise us too much that when we have cosine in the circle equation, that actually corresponds to symmetry around the x-axis, okay? And similarly, if we have sine in our circle equation in polar, that the sine actually corresponds to symmetry about the y-axis, okay? So even though it looks all different because we've got r's and thetas, it actually goes back to that same idea that x is the cosine and y is the sine, okay? And so we could kind of tell that even though these formulas alone are not super challenging, that even with what we've learned already, it was kind of hard to keep track of like, where's the symmetry and what is the shape? You know, so far we've only learned about circles and lines. And so that's why we had the table, okay? But we sort of finished off saying the table can be very long and tedious. And what we want to do is maybe just try a few points to get the idea of what the shape is going to be, okay? And so we didn't fill out the whole table for example number 6, but if we did, it would have given us more and more points on the blue circle that we have to the right, okay? So, what are we going to start with today? All right, we've got 2 more shapes to talk about. Okay, so one is the limacon. And what we're going to do with the limacon is we're going to take a look at different types that possibly happen. Okay, but we have the limacon. Usually, the equation looks something like this. Okay. Now, we'll notice that this equation has a cosine in it. So do we think it's going to be symmetric about the x-axis or the y-axis? Yeah, it's going to be symmetric about the x-axis. Perfect, okay? Now, what makes it different from the circle is we have a few other numbers in different places. And what I mean by that is we have this A in the front, and we could have a plus or minus in between. And then we have a B in front of the cosine theta. Okay, so it's not just a number cosine theta, but it's like A plus B cosine theta or A minus B cosine theta. Okay. Now there is another one where it is r equals a plus or minus b sine theta, okay? And it's going to give us all the same shapes, but this one, these limacons, should actually have symmetry about the y-axis. Okay, so the shapes and the progressions are going to be the same, except they're all going to be symmetric about the y-axis, all right? So what are all these shapes? All right. Well, it turns out, and let me kind of zoom in so we could see all 5 of them together. Okay. So it turns out that if you change A or B, and that's one of the things I ask you to do in the classwork, if you change A or B, and depending on how you change them, they're going to give you different versions of the Lima song. Okay. And so it turns out that it's all about the ratio for B over A. Okay. So let's go back and kind of look at what our B values and our A values are. So in this first case where there's something called a convex Lima song, what's the B value here? And what's the A value? Okay, so B is 1, good, because the number in front of cosine is 1, and A is 2 because the number that is not next to the cosine is a 2. So we've got an A of 1, which is sort of imaginary because we didn't write it. And then we have a, B of 1 and an A of 2. So what that means is that B over A equals 1 over 2. Okay. Now, when we're looking at this, what that means is that in this case, we're going to end up anytime this ratio is, actually, hold on, wait a second. So sorry. Let me check something real quick. I made the same mistake I did the last time. So sorry. Okay, so this is actually from, if you're curious about where it's going to go, in Calc 2, you do spend some time kind of going back over what we're learning right now. But depending on your instructor, you may or may not go over it super in depth, okay? I want to make one correction here, and during the break, I'm going to also change this in my notes so I don't make the same mistake again, okay? So the mistake here is that I was asking us to look for the B over A ratio, but what we really want to be looking for is the A over B ratio. Okay, so we want to switch those two. So if we take A and we divide it by B, we're going to get 2 over 1. Okay. So when we have this ratio of A over B, and that is greater than or equal to 2. Okay, so that ratio could be 2, it could be 2.5, it could be 10, it could be 100, but whatever that ratio is, if it's bigger than 2 or equal to 2, then what you'll get is a convex Lima song. Okay, and convex here really means that this side right here, okay, is actually kind of flattened, all right? So it means that one side is flat. So convex is just a fancy way of saying that one side is flattened, okay? But the way that we can predict that from the equation is we look at the A, which is our first number. Right? So let me just highlight that again. This A is going to be the top number in our ratio, and then the B is going to be the bottom number in the ratio. Okay. Well, what happens if we start to change these ratios? Okay. So if we look at this second one, the one that says dimpled limmason, what is our A and what is our B? Okay. What is our A and what is our B? 1.3 for our A, and our B happens to be 1 again. And so when we take that ratio, A divided by B, we'll get 1.3 over 1, which is 1.3. Okay. And so when we get 1.3, is that number less? It's less than 2, right? But it also happens to be greater than 1. And so that's what happens if we have a ratio of A over B. And it is bigger than 1, but it's also less than 2. What's going to happen is that part that was flat in the convex limmason is actually going to start to create a little corner here, okay? Now, if we kind of keep going down, let's fill in these other ratios and see what we get. Okay. So for the cardioid, well, what's our A? That's 1. What's our B? That's 1. So A over B equals 1 over 1. Okay. This is one of the most special cases for the limmason. It's called a cardioid. And it's called a cardioid because it looks like a heart. Okay. So cardioid, you want to think it looks like a heart. All right. And that is a special case that happens only when A over B equals 1. All right. So the ratio of those is 1, or the A and B are exactly the same, you're going to get a heart. Okay. All right, so we can sort of see this progression here where the convex one was flat on one side, then the dimpled one was a little bit of a corner, and then we get the full heart when we're looking exactly at 1, okay? Now, I know that these look like butts, okay? I have heard that many times, which is exactly why I turn them sideways. There's a reason we're doing the cosine ones, because when you do the sine ones, they're all facing up and down. It looks a lot more like a butt, okay? But we're here to, the words here come from the fact that it looks like a heart, okay? So whatever is happening in your brain right now, laugh about it, it's fine. But when we're talking about cardioids, it looks like a heart, okay? All right. Now, the last two cases here, all right, the last two cases, what happens with these ratios? So A in this case is 0.5 and B is 1. So when I divide A by B, I actually get 0.5, okay? So 0.5, well, that is less than 1, okay? So A over B is going to be less than 1, but it's also going to be greater than 0, okay? And those, when you start to change that ratio to be a fraction between 0 and 1, you get this new part, which is like we call it an inner loop. Okay, so we get sort of the cardioid with the bonus inner loop. Okay. And so one of the things that you'll learn about in Calc 2 is like, how do you find the area maybe inside of the whole cardioid? So that'll be pretty neat. And then you might even see some of the more challenging problems that are like, don't find the area of the whole cardioid, but just in the inner loop. Or just outside of the inner loop, okay? So when you're thinking about applications of it, we're really looking for like, how do we find area, all right? Another application that you'll look at is like, how do you find out the arc length or how long around or the circumference of the shape? Okay, so those are going to be some applications that you can sort of look forward to, all right? All right, so we've got one last case, and this one should look pretty familiar. We've got a circle, okay? But let's think about our A and B values. So A in this case is 0, and B is 1. And so when I take A and I divide it by B, I'm going to get 0. So another special case is when that ratio equals 0, we actually get back to the circle, okay? And so when we think about these, a circle, even though we learned that earlier, is actually a special case of the cardioid. It's a special case where the A value is 0, and so we end up with a circle. Like none of the sides are dimpled or convex. It's just round. Okay, there's no inner loop, none of the other fancy features. It's like the most basic cardioid, okay? Or limacon, rather. So you can sort of look at these all with the sine function as well. So A plus B sine theta. And when you have the sine theta, the only thing that's going to change is that the symmetry will be about the y-axis and not the x-axis. Okay. Any questions about these 5 shapes so far? Okay. All right. So I wanted to do a few examples where we use our table, we kind of plot some things, okay, and think about what things look like. So in looking at example 7, maybe let's list out some things first. What can you tell me about the symmetry of this shape? It's symmetric about the x-axis, exactly. I see the cosine, I know it's symmetric about the x-axis, okay? Now we can also think about the B or the A over B ratio. So the ratio is going to be 4 over 2, and that's going to be 2. Okay. So from our ratio, which one of those 5 shapes from above should we anticipate here? Yeah, this ratio is going to give us a convex limacon. Okay. All right. So we kind of know what it's going to look like. Um, and what we can do to figure out exactly like how big this is, like how far out does it go on the x-axis, how far up does it go on the y, is let's plot some points and kind of see. Okay. So I think it's always nice to throw the 0 in there to see. So I put in 0. Cosine of 0 is 1. So 4 minus 2 gives us 2. Okay. That means the first point we want to plot is 2 comma 0. And so when I go to my graph, we're going to have, I'm going to go along the 0 and I'm going to go 2 circles out, which means that point right there. Okay, so this is our first point. Okay. So let's try pi over 4 and see what happens. Okay. So we're going to need a calculator to help us figure out like the actual decimal, but this should be 4 minus 2 root 2 over 2. And let's see what that gives us. That's going to give us an R value of about 2.6 comma pi over 4. Okay. And this one will be our second point. So I'm going to go to pi over 4 and I'm going to go out 1, 2, and a little bit more than half. And that's my second point. Okay. Okay. Well, let's plug in pi over 2. See what that gets us. So pi over 2, let's see, cosine of pi over 2 is 0. So 4 minus 0 gives me 4. And so I'll get 4 comma pi over 2 as my third point. So I'm going to go to pi over 2 and go up 1, 2, 3, 4. And let's take a moment and do some of the other ones. 3 pi over 4, pi. Let's see, 3 pi over 4 has a cosine that's negative, so 4 plus 2 over root 2 over 2. So 4 plus root 2. That gets us 5.4-ish, comma 3 pi over 4. And that's going to be the fourth point we plot. So let's see where that is. 3 pi over 4. And I'm going out 1, 2, 3, 4, 5. And I made it off the grid. Wonderful. All right, and let's get that pi in there. So pi is, cosine of pi is -1, so that's 4 plus 2 or 6. So I have 6 comma pi for the fifth point, and good job, Judy. That's off the grid. 1, 2, 3, 4, 5, 6 is about here. Okay. So you can do your own calculations, but you start to see something like this. Okay. Now, I could think about whether or not I've gotten my entire shape so far, right? Because according to when we did the circle, I went from 0 to pi and I got the whole shape. I went from 0 to pi here. Do I have the whole shape? Do I have the whole convex limacon? No, it looks like I just have the top half, right? Looks like I just have the top half. So if I think about connecting these points, I might get something that kind of looks like this. Okay, that's a terrible job, but you get the idea. Since I know that it's symmetric, I could actually plot some of the points in symmetry about that axis. Then I don't need to go and find all the other values. Okay, so the other points that I've drawn right now, I could find from the table, or I could say, hey, I know this is symmetric about the x-axis, so let me just plot the top half, and then I can just reflect it and draw the bottom half. I don't know if this bottom half is going to go much better here, but we'll see. Definitely not. We'll chalk this up to one of the worst drawings that we've had here, okay? But this has, if I had drawn it better, like a little bit of a flat side at the pink point, okay? And yeah, I feel like you folks, I mean, most of you know that like I'm using, you draw the circle, you hold it, it becomes a perfect circle. You've not seen my actual like whiteboard work, and it's not good. Okay. But we can sort of use these points along with what we know in order to sketch a picture of the shape that we have. Okay. But I think this is a good example to say, like on a test or a quiz, like I'm not judging how well you draw your shape, as long as you can show me, hey, I know what points went into it. I just can't draw very well. Like that's okay. Okay. Well, thank you, Vanessa. You're very kind. All right. But it's kind of neat to think about like I told you about these patterns, right? I was like, hey, just believe me. If you have these ratios, this is what's going to happen. But when we actually just went back to our good old plotting points, like plugging numbers into an equation and seeing what comes out, it turns out we were able to confirm those things. Okay. And so when you go and do your Desmos activity, you won't have to draw. You're just going to be able to type equations in, do a quick screenshot, and just show me what you get. But the point with that activity is like, how do you think about those patterns? Okay. All right. Let's go ahead. Should we try one more? One more Lima song? Yeah, this one is going to be a sine one. Okay, so I think it's probably good to go over. So as soon as we see that sine, we're thinking that this one has symmetry about the y-axis, right? We're thinking symmetry about the y-axis because we know that sine is the y values on the unit circle, okay? And while we're here, it'd probably be good to calculate our A over B ratio. So we know where on the spectrum of limacons this one falls. And so we'll get A of 3 over 3, which gives us 1, which means that we have a cardioid. Okay. So we're going to have that heart-shaped curve. All right, and let's kind of plot a few points to see what happens. And maybe even what do those numbers tell us? Like the 3 and the -3 actually correspond to certain points on our graph. Okay, so let's start with 0. So if I plug in 0 for theta, I'm going to get -3. So that first point is -3, 0. So I go to 0 and I go 3 in the opposite direction. Okay. That's a really good question. I'm so glad you folks asked that. Okay, so do you not include the negative for the ratio? And that is correct. We don't include the negative for the ratio. And some textbooks even say take the absolute value of that ratio. Okay, the ratio gives us the shape. The negative actually tells us more about whether it's facing like to the right or facing to the left. Okay. Or if it's an up or down one, the negative might tell us, does it face up or does it face down? All right, so I'll give you a moment to write that down, that when we're looking at the ratio, we're actually looking at the absolute value to tell us the which shape it's going to be. Let's plug in some more points. See what we get. Let's see, sine of pi over 2 is 1, so negative 3 plus 3 is 0. Sine of pi is 0, so that gets us back to negative 3. Okay, now we'll do the decimal ones. All right, pi over 4, let's see, that's negative 3 plus 3 root 2 over 2. Let's see what decimal that gives us. Negative 0.9 comma pi over 4. Okay. And so let's plot, let's figure out the other one first. So let's see, sine of 3 pi over 4 is the same as sine of pi over 4. So we'll actually get the same R value. Okay. Now you can do all of this on Desmos or on your calculator. It'll help you figure out those points a little bit faster. But I just wanted to sort of write that out so you could see like how you might figure those out. But now let's plot those points. So I'm going to go to the orange one. So I'm going to go pi over 4, but I'm going to go 0.9 in the opposite direction. So like here. I'm going to go to 0 or pi over 2, but I'm going 0 out. So that's going to stay at the center. Let's see. All right. I'm going to go to 3 pi over 4, and I'm going to go 0.9 in the other direction. And then the last point I'm going to draw here is I'm going to go pi, but I'm going to go 3 in the other direction. Now, I think we can see here that we don't have a whole cardioid, right? We have part of the cardioid. But can I use symmetry here? Can I use symmetry of the x-axis to draw the rest of it? No. Okay. Now, that's something that's going to actually be really important to think about, symmetry. Okay. So we already said at the beginning, this is symmetry about the y-axis. So the part that we draw down here, okay, if we were to sort of connect the, okay, the bottom of the heart, then we cannot just do this where we do the same thing on the top, okay, because it doesn't have that kind of symmetry. So in this case, what we should do is actually, yeah, it would be eyes instead of a heart, right? I'm sure there's some inspirational quote there about love and heart, but I cannot think of it right now. So if we're trying to think about all the other points, then let's plot a few more, okay? So let's go to the 5 pi over 4, the 3 pi over 2, the 7 pi over 4, and the 2 pi. let's see, 3 pi over 2, the sign of that is -1, so -3 minus 3 will give me -6. So let's actually get that point in there first. So I'm going to go to 3 pi over 2, and I'm going to go 6. 1, 2, 3, 4, 5, 6. Okay. So that red point, that is off the grid. All right. That red point is actually the highest point in the entire curve. I could plot the other points right now. I could find what happens what is R when sine or when theta is 5 pi over 4, what is R when theta is 7 pi over 4. I could find all those other points, but I actually think that one point gives us enough to sketch with symmetry, because all we need to do is sort of connect this part up to that red point and then kind of come back around. Okay. Now, if I had thought more carefully about the symmetry, check out what I could have done. I could have graphed these 5 points. Pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2. Okay. If I had graphed those points, what I would have found is the right half to the heart. If I have the right half of the heart, I can draw the left half of the heart because I know there's symmetry about the y-axis. Okay. This is definitely bonus level kind of thinking. You don't have to be, super creative in how you pick your points. But if you're like the kind of person who's like always looking for shortcuts, this is somewhere you can actually start, is thinking about what points would be valuable to plot. Okay. Because it's not worth cranking through a whole bunch of numbers if some of them don't give you the symmetry you need, right? So in this case, if I plotted pi over 2 to 3 pi over 2, I could find the right half and then the left half. But if I think about that same reasoning for 7, if we did 0 to pi, that actually gave us the top half of our Lima song. Okay. No, I would say like this point right here is at pi over 2 and it's not at the origin. So got to be careful about generalizing. Okay, so yes, but if you have, what happens if you have cosine in there? Cosine of pi over 2 is not 0. You can have a cardioid with cosine. It doesn't have to be a cardioid with sine. There is going to be a point at the origin, but you don't always know where it is, right? It could be pi over 2. It could be pi, depending on your equation. Okay. Yeah. Okay, so yeah, for cosine, you could say, let's start at 0. And for sine, starting at pi over 2 might be a good thing to do. Yeah, exactly. And actually, for those of us who might be wanting to connect the dots even more, remember when we learned about inverse cosine? And I said for inverse cosine, you got to pick from the top half of the unit circle. That 0 to pi actually is sort of the same values you would want to try for the cardioids or the limacons. But if you think about inverse sine, I told you to choose from the right half of the unit circle, which technically was negative pi over 2 to pi over 2, right? But we could also call that pi over 2 to 3 pi over 2, right? So it does kind of go back to that inverse sine and inverse cosine, like which parts you choose from. That symmetry actually carries through to these polar graphs. Yeah. Mm-hmm. Mm-hmm. You're thinking about like the graph transformations for sure. All right. So for better or for worse, I think all of this connects, right? So we can think about it like none of it ever really goes away. But the good news is if you really understand that beginning part, the more you learn, the more it tightens all those connections. Okay. Exactly. Exactly. We're weaving together a very tight knit group of concepts here. Well, on that note, it seems like a good time to take a break. Okay. So when we come back from break, what we're going to do, just so we can, oh, are you going to drop a link in there? Do you have it typed out? Do you want to share your screen? Or should everyone just kind of type it in themselves? You can check it out over break. Okay. All right. Well, real quick before we leave, when we come back, we're going to talk about rose curves. So that is the last kind of graph we're going to take a look at. We're going to look at how we plot those and thinking about numbers of petals and things like that, because we're looking at flower types of graphs. But yeah, Eric, if you want to share that graph before we go on break, it could be a nice thing for us to look at before we do that. Oh, you're not allowed to. Can you now? Oh, it's like a butterfly. Cool. Well, so this is sort of why I wanted the last two math and writing assignments to be this art project, right? This polar art project, because there are so many cool things that you can design on here. And I know we've learned a lot about graph transformations, like if you change this number, then it does this. And that's kind of interesting and it applies here, but in this case you get to change these numbers and see what happens, and it actually creates something that is maybe visually more appealing. Okay, so all right, so it is 10:47. Let's be back at 11 o'clock. All right, we'll come back at 11 from break. All right, so I'll see you folks back here at 11. Aaron, we expect an update on that, see how that goes. Recording. And I'm gonna go ahead and share my screen. Okay. Does everyone see the Desmos? Hopefully I'm not accidentally projecting everyone's grades. Okay, great. Okay, so normally when we come into Desmos, we look for like the XY grid, and that's just sort of like the basic one that shows up. But if you don't know by now, this little wrench in the corner, so the graph settings, if you click on that, you can actually change a bunch of stuff. And so what we're going to do is we're going to click on the grid that is the polar grid. Okay, so not the rectangular or Cartesian, but we're going to click on the polar. Okay. And so now you see a graph that looks like the graph paper that we've been using in class. Okay. Okay, so let's do this. So rose curves have a special kind of equation. They're of the form r equals, and we have a number in the front. So let's make that number 3. And then it either has sine or cosine, all right? So let's do the sine one first, okay? Now it says sine of n theta. Now n is another number, okay? So let's say that n is 2, and then if you want theta, you can type in theta, and it pops up as theta. Okay, kind of like if you type in pi for pi, it will give you the symbol for pi. Okay, so again, if you want to find the theta, you can just type in theta, and it will turn it into theta. All right, so let's take a look at this graph. All right, so we've got this 3 sine of 2 theta. All right, now there's a number in front of the theta, so we know that it's not just going to be a circle, right? So if I didn't have the 2, whoops, if I didn't have the 2, it would be the circle, right? That's what we learned a couple sections ago. But as soon as I have the 2 in here, it's not a circle anymore, right? And we start to get these flower-like shapes that give you different petals, okay? So question for you folks, how long is each petal? Or what's the, not radius, but like how many circles do we go out for each petal here? 3, okay. And check out what this first number was. It was a 3, okay? What do you think happens if I change that number to a 5? It will go out 5 circles. Okay, so let me just change that to a 5. Whoa, now we have like a bigger flower, okay? So if you're thinking about some of your art project stuff, you could maybe do like, you can almost have them nested inside of each other, okay? So the coefficient defines the size, but let's be more specific about that. The coefficient determines the petal length, okay? So the coefficient determines the petal length, all right? Now, let me just hide this one for a moment. If we look at just the red one, okay, just the red one, this number in here was 2. How many petals are there? There are 4 petals. Okay. Let's see. If I put in a 4 here, instead of 2 theta, I have 4 theta. How many petals do you think there will be? Okay. Let's see if Eric is correct. I'm going to change this 2 to a 4. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. 8 petals. Okay. What do you think if I change the 4 to a 6? How many petals do you think? Okay, let's see. 6. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12 petals. Okay, let's try an odd number. All right, I like this. I like this. So before we go to the odd numbers, though, let's put the 2 back in. This is symmetric about which axis? The y. And it happens to be the y and the x, okay? What happened when I changed it to 4? Is it still symmetric about the y and the x? Yeah, okay. And when I went to 6, it's symmetric about the y and the x. Okay. Now, let's see what happens if I make this number an odd number. So let's say 3. If I put in a 3 in front of the theta, how many petals do you think we'll have? 5. 6, 6. Okay, ready? Okay, but here's the thing. You guys are right. There are 6 petals. Huh. They are 3 petals and another 3 petals that are on top of each other. Yes, they are overlapping. Okay, so there are 6 petals, but 3 of them are hiding underneath the other 3. Okay. Remember when we did the circle earlier and I said, oh, if you go from 0 to pi, you actually get the whole circle? And so if you go from 0 to 2 pi, you actually had 2 circles right on top of each other. This is like that same idea, okay? I love that you brought this up. That was actually my next question. So how you can tell the parent function, which is sine, is symmetric about the y-axis, right? So the fact that there is sine, there's going to be symmetry about the y-axis. And that's guaranteed whether n is even or odd, okay? Well, Yitan, I think that would be a really great thing to play around with. How do you offset them so you can see all more petals, okay? 3.1. Whoa. So maybe Yitan, that sort of answers your question about what happens to offset some of those, okay? So let's see what happens when we type in 5 here. Okay, if I type in a 5 as my coefficient for theta, I should get 10 petals, but 5 of them are going to be on top of the other 5. And it should have symmetry about the y-axis, and it does. Okay. All right, let's see what happens here if we change this to cosine. All right, 5 petals, actually 10 petals, right? Which is 5 are on top of the other 5. Yes, yes. Okay, so that's the part that's different. Now, because I changed it to cosine, this graph, it still has 5 petals. Each petal length is still 5, but the symmetry is different. It is symmetric about the x-axis, okay? So sometimes you get to Calc 2 and your professor's like, all right, let's draw a quick sketch. And you're like, how do I know what it looks like? You kind of have to remember these ideas that if it's cosine, you know the symmetries around the x-axis. If it's sine, you know it has symmetry about the y-axis, and then you can kind of go from there. Other than that, all of these petals are going to be evenly spaced out, okay? Yeah, exactly, exactly, all right? Okay, so there are some spirals. If you look up Archimedes spiral, that is a shape that we're actually not going to get to. But if you just have r equals theta, okay, you actually get a spiral. Kind of zoom out a little bit, okay? If you want to make your spiral keep going, any ideas on how you could do that? How might we get a spiral to keep going? You should actually multiply the theta, but you see how every time we're typing in these, there's this little bar down here, it's kind of grayed out, where it says theta goes from 0 to 12 pi. Let's see what happens if we change it to pi. Yeah, if we only go to pi, it's only going to do a little tiny part of the spiral. But if you do like 100 pi, or if you do 50 pi, well, 50 pi. You could get something a little bit more, right? Any ideas on how you could make the spiral go in the other direction? Yeah, ready? Check this out. I have my r equals theta, but what if I do r equals negative theta? It goes in the other direction, okay? Now, if you're interested for your art project, if you click on the, don't click on it, but sort of like click and hold on this part, you can change the color of the graph. So if you want them both to be red, you can make them both red like that. If you want to make dotted lines, you could do a dotted line instead. Okay. If you want to change the thickness of the line or any of that, you can change those numbers over here. So I could make that line really thick. I could change it to a different color. Okay. So lots of options that you can do to play around with. Oh, for sure. This art project is very like open-ended. Okay. All right, so yeah, if you put any A in here, anytime you add a slider, okay, that allows you to kind of play what happens with all the different values, okay? So I think I do ask you to play around with the slider in that classwork that's due today so you can kind of see, kind of like we're talking here now, like what happens when we change this? What happens when you change that, okay? Yeah, that's pretty cool. So it's really pretty, that's for sure. It's definitely, I think, prettier than the other graphs we've learned. But so much of what we learn about graphs actually comes back to kind of help us here. All right. Mhm. So like that's pretty cool too. Yeah. All right. It does kind of look like an onion. These are all super good questions, right? Are there asymptotes? What are things that happen with polar graphs? And I encourage you to kind of explore that and see what you can find, okay? All right, so let me stop sharing this for a moment. Let's go back to our notes, which is really meant to just be like a little bit of a organizer for the different cases, okay? I'm gonna stop sharing that and I'm gonna share my note page back up. So, so what we were exploring before we got lost in the spiral business is we were taking a look at rose curves. Okay, so rose curves have that form that we talked about earlier, which is a sine of n theta. Okay, and that one we know is going to have symmetry about the y-axis. Okay. And our other one, the one with cosine, same form, a cosine n theta is going to be symmetry about the x-axis. Okay. And so I broke it down into case one and case two so we could take a look at the even and odd of n. Okay. So let's say for case one that n is even. All right. And so when n is even, you will see 2n petals, right? We'll see twice as many petals as the number for n, okay? But it is going to be symmetric about the y-axis, meaning that whatever we get on this side will be the same as whatever we get on this side. And I know this is not a picture of a rose curve, but we'll get some pictures when we plot sort of a table out, and you'll have a chance to look at actual pictures in that classwork number 7, okay? Now, if we have n is even and its cosine, the only thing that changes, we're still going to have 2n petals, but our symmetry is going to be across the x-axis. Okay, so our lines of symmetry are just different, but either way, we'll have twice as many petals as the number in the equation. Okay? The last thing I want to have us write down for this is that A equals the petal length. All right, so that number A is how long the petal is. Right. Now we can say something very similar for case 2, except that n is odd. So the symmetry is the same, the petal length is the same, except there are 2n petals, you just don't see them all, okay? So maybe we write that down. There are 2n petals, but you only see n. Okay, you only see n of them because they're superimposed on top of each other. Okay. The symmetry part is the same though. Anything with sine is going to have symmetry about the y-axis, and anything with cosine is going to have symmetry about the x-axis. All right, so let's practice these tables one more time. And I actually meant to leave more space. I wonder if I can still do this. But I guess I can't get rid of that one, huh? Okay. Sorry. All right. So let's take a look at number 9, okay? And we're gonna plot some points, but what we're gonna do is really bring back that idea of equation solving that we had in chapter 7, okay? So with the rose curves, sometimes when you plot points, okay, what happens is you go back and forth between the end of the petal and the center, and then the end of the petal and the center. So let's just kind of try out some values and see what happens. So if I plug in 0 for theta, we get 4 sine of 0, which is 0. So I get 0, comma 0. Okay, so if this were my first point, I would have a point right at the origin. Okay. Now we've been trying pi over 4, okay? But let's sort of skip that for a moment. Let's say we went to pi over 2. Pi over 2, this would give me 4 sine of 2 times pi over 2. Let's see, that's 0. So 0, comma pi over 2. So this point is right back at the origin. Okay. So what do you think is going to happen if I plug in pi and 3 pi over 2 and 2 pi? Yeah, they're still going to be at the origin, right? So even if you make a table here, I'm going to end up with a bunch of points at the origin. Well, that's not very useful if I'm trying to plot, because then I think it's just like one big point at the origin, right? So how you pick the points in between actually comes from our equation solving. Okay, so I'm going to see, maybe I have enough room to do it up here. Let's do it up here. So this will be example 9. Okay. So example 9, the one we were just looking at, we have r equals 4 sine of 2 theta. Okay. So let's say that it had been a long time since you took this class and you're like, I don't remember what that looks like. Let me plot a few points. And you make your table and you end up with a whole bunch of points at the origin, right? Maybe one thing you would remember though is how long is each petal? Okay, so that first number is going to tell us the length of the petal. Okay, so what I'm going to do here is I'm going to say, let's find the angles where the end of a petal, ends of petals are. Okay. So what I mean by that is, like, you think about the petal, if you know where the end of the petal is, then you can sort of sketch the petal, right? You know the direction, you know all of that stuff. So let's find out where the ends of the petal are. So in order to do that, you know that the longest that the petal can be is this number. And so what we're going to do is we're going to set up an equation where it's 4 equals 4 sine of 2 theta. Okay, the 4, because this 4 is the end of the petal. Does that make sense there? Okay. So if I want to know like where the end of the petal is, I want to say it's going to be at the 4th circle out. So the 4th circle out is when r equals 4. Okay, and whatever angle that's at, that will tell me where the end of the petal is. I know it's at 4, but the question is like what angle, okay? All right, so let's solve an equation here, okay? Now, I know that this looks like the double angle, right? Because we have sine of 2 theta. But if there's only one trig function, so there's only the sine of 2 theta, we're not trying to match it to any other thing, it's not a quadratic version, then our best bet is to go ahead and isolate the sine 2 theta, okay? So if I isolate the sine 2 theta, I'm going to get 4 divided by 4, or I'm going to get 1. Okay. Now let's think about how this equation could be true. Like, how do we make, like, what angles make this true? Okay. And what we can do is we can leverage that general solution piece that we used in the last chapter. Okay. So we could say that 2 theta is, let's see, sine is 1 at pi over 2 plus 2 pi k, where k is an element of the integers. Okay. Now I could get theta by dividing everything by 2. Theta equals pi over 4 plus pi k, where k is an element of the integer. Okay. So let's see what values those are. I know one of them is pi, but what is the angle going to be when k equals 1? Like if we add pi over 4 to it, what do we get? Or if we add pi to it, what do we get? We get 5 pi over 4. Good. And so what we can do from here is we can go ahead and find those two angles. Okay. And what that means is that at the angle pi over 4, the R value is 4. That's like one end of one petal. Okay, so this is the end of one petal. Now this gives us 5 pi over 4, comma 4. That gives us the end of another petal. Okay. So let me just kind of pause here for a moment. Does this make sense to folks? Like, I know we know how to solve equations, but the fact that we're finding sort of like where the ends of these petals are going to be important to help us graphing things. Okay, because sometimes with the table we found out we were just getting points at the origin, right? So let's go ahead and plot these 2 points, pi over 4, comma 4, and 5 pi over 4, comma 4. And so when we plot those, let's maybe do this one in green. So pi over 4, comma 4, 1, 2, 3, 4. Okay. And let's do this one, 5 pi over 4, comma 4 in blue. 2, 3, 4. Okay. So what I have here is if I put that back into the table at pi over 4, I'm going to get 4. And that will give me 4, comma pi over 4. Oops, I wrote those backwards. Sorry. Okay. So let's think about the order in which this happens. I go from the pink dot to actually the blue dot. Oh, sorry, the green dot. And then back to the orange dot, right? So pink and then blue and pink and then green and then orange, okay? So that means that my petal is gonna look something like this. Okay, good. And because it's sine, once you've got that first petal, just got to divide it all up evenly. We know that it's symmetric around the y-axis. Exactly. So the next place it goes, if I were to think about 3 pi over 4, all right, I bet we're going to get 3 pi. I believe we're going to get 4, comma 3 pi over 4. That would be like here, and then I could go like this, okay? And then I could go to the blue dot, and then I bet there's gonna be one more here because I know there has to be 4. And I am double checking that indeed we have symmetry about the y-axis, okay? So I know earlier that Richard was talking about like how can we sort of shortcut things. Like for cosine, it's probably good to start at 0. For sine, it might be good to start at pi over 2. But when we're thinking about different shapes, the strategies sort of change, right? If I were drawing this and I forgot what it looked like, but I knew it was like it had petals, if I just graph the first 3 points, that's going to give me the first petal, and that might be enough for me to sketch the rest of it, and then I don't need all the other values. I kind of just know when they're going to happen because I can look at the picture and just draw it, okay? But you can always fill out every single value in your table if you want to make it like more accurate. That's absolutely fine. Okay. All right. So let's take a look at this last question over here. Okay, so I'm not going to use this one. I'm going to use the copy. Where did the copy go? Oh, down here. I'm going to use the copy down here so I can just write the equation right below. Okay. But if we think about equation or example number 10, I have the cosine here, okay? So let's see what we can predict based off of the equation. Well, we know that it's going to be symmetric about the x-axis, right? And let's call it a petal length, not a radius, but a petal length of 2, okay? And how many petals will we see? Yeah, there are 6 petals, but we only see 3. Exactly. Okay. All right, so let's plug in some values and see if they're giving us anything first, right? So I'm going to plug in 0. Let's see, 2 times cosine of 3 times 0 is 0. Cosine of 0 is 1, so this will give me 2 comma 0. Okay, so this will be our first point. We know it's going to be along the 0 angle and 2 circles out. Okay. Now let's use the equation solving to kind of help us think where the other petals might have their ends. Okay, we found the end of one petal. And because I know it's symmetric about the x-axis, I can actually go ahead and draw in this petal. Okay. Well, let's practice that equation solving. So we have r equals 2 cosine of 3 theta. Now, how do we set up our equation so that we'll find the angles for the end of the petals? Exactly. We're going to say, well, the end is going to be at the second circle out. So we're going to replace r with 2. Perfect. Okay. Now we're going to do the same thing we did before. We're going to isolate our cosine, and then we get 2 divided by 2, which gives us 1. Okay. Now we're going to leverage our general solution to help us find the solution. Okay. So what we know is that 3 theta is going to be 0 plus 2 pi k, because 0 And every time around the circle is everywhere cosine equals 1. Okay. And now I'm going to divide by 3. And so if I were to list out all the ones that fit one time around the unit circle, I would get 0, 2 pi over 3, 4 pi over 3. Now there are 3 values here. That's actually really good because we said there were going to be 3 petals that we see, right? So if we got more than 3 answers, that might be a little suspicious because we know there's only going to be 3 that we see, right? So that means that 1 petal is going to be the first one we found, which is 2, 0. The second petal is going to be 2, 2 pi over 3, and the third petal will be at 2, 4 pi over 3. And those are the ends of the petals, right? So let's figure out where those are. 2 pi over 3, we're going to go out 2. That'll be 1 more petal. And then 4 pi over 3, go out 2 units. That's another petal. Okay. So when you're looking at these petals, here's what I want us to remember. Normally, we've been doing pi over 4, pi over 2, blah, 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 blah. But in this case, if we had picked pi over 4 and pi over 2, we would not have gotten the ends of the petals, right? That's a problem. So when you're doing the table, it's really important for us to think about what values are useful, okay? So when you fill in this part, you want to find or use valuable points. And by valuable, I just mean like it better be a point that helps you get important information, right? If you're plotting pi over 4 or pi over 2, you might just get a bunch of weird decimal things. It's going to be hard to see the picture. So we got to pick points that are going to give us the picture we want to see, okay? Is this going to be on the quiz and exam? Absolutely. Do you expect us to do the general solution stuff? 100%. Okay. I know we're in a time in the classroom right now where we can use calculators for everything, but I think it's important to consider that at some point in your math career that might stop. I don't want us to get back into the classroom and be like, oh shoot, I only know how to do this when I have a calculator in front of me. Okay. Also, what a great way to study for the final. Thank you, Judy, for reminding us of things that might be important for that final exam. All right, so that brings us to the end of 8.4, okay? So I'm gonna stop the recording right now.